In this video, I will be explaining the concept of general annuities. I will be starting reminding you what is an annuity. An annuity is a series of equal payments made at regular interval of times. So you can see the time as a line. If you see that, an annuity looks like this. These are, that appears here, are the payments that are made at a regular interval of time. So an annuity involves several quantities. The first one is the payment, R. So the payment is this amount that I have symbolized here by R. It also involves the total number of payments, and I'm going to symbolize this with the letter N. We have also the payment period, so the length of time between two payments, and this payment period is usually a month or a quarter, 3 months, or half a year. So the time between two consecutive payments is the payment period or the payment interval. So they are usually monthly, quarterly, semi-annually, annually, but could be daily or weekly or bi-weekly. So this is one period, but there is another period that is the conversion period. And the conversion period is the time of conversion of interest. So the interest, because there are money and time involved here, there will be some interest. And the conversion of this interest is what we call the conversion period. So the conversion period could be a month, a quarter, a semi-annual period, or an annual period. So it could be a year, or half a year, or a quarter, that are 3 months, etc. So in an annuity always we have two periods, two important periods, the payment period and the conversion period. And we have also the term. And the term, it will be the length of time between the beginning of the first payment interval to the end of the last payment interval. And we're going to symbolize this by T. So this will be the term. So this is an annuity. But what is a general annuity? If this payment period and this conversion periods are different, so that we say that we have a general annuity. So an annuity is said to be a general annuity if the payment period and the conversion periods are different. We are going to work today an example of a general annuity, but this general annuity will be also ordinary annuity. An annuity is ordinary if the payments are made at the end of each payment interval. For example, you see here this annuity that I have symbolized in this line. You see that the payment was at the end of this first payment interval. The second payment is made at the end of the second payment interval, and etc. The annuity finishes always in a payment. So the last payment interval finishes with that payment. So this is an example of an ordinary annuity. So we are going to be working a problem in which we have an ordinary general annuity. What to do to solve a problem when the payment period and the conversion periods are different. So that's what we're going to work today. So let's see. What will deposit of $60 made at the end of each month amount to after 6 years if interest is 4.8% compounded quarterly? You see here that there are payments of $60 made at a regular interval of time, so made at every month. And also we see that there is another interval here, that is the conversion interval. The interest is 4.8 compounded quarterly. So we have a problem of a general annuity because the payment period is a month, the conversion period is a quarter. And it's also an example of an ordinary annuity because the payments are made at the end of each month. So this is an example of an ordinary general annuity. What to do in this case? So we have this situation. During 6 years, we are making payment of $60. And they are asking me, what will these deposits amount after 6 years? So we want to know what is the future value of this annuity. And we have some information. We have that the payments that I call R is equal $60. So R equals $60. We have also that the payment per year, and I'm going to call it K, is equal 12. So I can now compute how many payments in total. So I can compute N. So N will be 6 times 12. So I go compute N, the time, the term, multiplied by the number, the term in years, multiplied by the number of payment per years. It will be 6 times 12, that gives me 72. So we have 72 payments, so we know n equals 72. We know also that the rate of interest is 4.8%, and this is compounded quarterly. So we have another number of periods per year, and this is the number of conversion periods per year. The number of conversion periods per year are 4, so we say that m equals 4. So this is the information that we have in this annuity. We see in this example that the payment periods per year is different than the conversion periods per year. So it means that k is different than m. And anytime that we see that k, I'm going to symbolize k by the number of payment periods per year. M is the number of conversion periods per year. And these numbers are different. This is a general annuity. What to do to solve a problem like this? We already studied how to compute the future value of a simple annuity. In a simple annuity, the payment periods and the compound periods are the same. And we know that the future value of an annuity like this is the future value equal the payment multiplied by 1 plus I to the power n minus 1 divided by I. But what happens if the two periods are different? When the payment interval and the conversion interval are the same, so this I represents the periodic interest, the interest per period of time. But in this case, we have two different periods. So what to do? The idea is to find an interest, to find an I that will be equivalent to the rate of interest that we have, but compound 12 times per year. So that compound as many times as the number of payment periods we have. So in this case, we're going to compute an I, an equivalent periodic rate of interest, monthly rate of interest, that is equivalent to this 4.8 compounded quarterly. So in this case, we're going to have an annuity that have the same number of compounded periods and payment periods. In this case, we're going to have an I that is compounded as many times as the payment periods per year. So if we put $1 per 1 year and an interest compounded monthly, so what we're going to have is 1 multiplied by 1 plus I to the power k. If k is 12, for example, this will be the interest in 1 year. And that must be equivalent to what we have if we put $1 at this rate of interest compounded m times per year. So 4 times per year in this case. So that's what we're going to do. Find an I that is equivalent to this R. This I is compounded k times per year. This R is compounded m times per year. So in this case, we divide the nominal rate of interest by m to get the periodic rate of interest. This I is already a periodic rate of interest compounded monthly. So this I will be 1 nominal rate of interest divided by 12. But let's just compute the periodic rate of interest, the rate of interest compounded monthly. So one idea is just divide both exponents, both sides by k. So in this case will be 1 plus I, just because will be k divided by k equal 1, the exponent. And the other side will be 1 plus r over m to the power m divided by k. So we're going to have this. And this 1 go to the other side, so we have that I equal this expression minus 1. So this is the I that we're going to be using in the formula of future value. Let's do that in this example. So if we have this example, if we want to know, if we want to compute the future value, so how much amount these 72 payments at the end, so what we're going to do is just use this formula with this I. And the I will be given by this formula. So I just make a substitution. This R is 0.04.8, this M is 4, and this K that appears in the formula is 12 payment periods per year. And I will be using a calculator for doing that. Let's take out the calculator. Anytime that I press a key here, it will be appearing the key that I press at the side of the calculator. So let's draw this line here to separate the key that I'm pressing with the formula that I have. Okay, so I see the formula is have a bracket at the beginning, so I open a bracket, and you can see the bracket in the screen of the calculator. You can see also the bracket I press here. So Then after the bracket we have a number 1, so 1 plus, then r divided by m, but r is 0.048, so it will be 0.048 divided by 4. So we have that m equal 4. So I divide it by 4 and close the bracket. So I close the bracket. The calculator now is able to make the operation that is inside the bracket. But I noticed that they say to the power m over k. So I will be raising this to the power k. This is the key for power, so I'm going to press the key for power and open bracket. Anytime that we have an operation in the exponent, it will be, we have a calculator like this, this will be a good idea to put this operation in bracket. So I'm going to open bracket and then say m is 4, so 4 divided by k, and the number k equal 12. So this will be divided by 12 and close the bracket. So in this way I put the exponent in bracket and then minus 1. So I press minus 1. So I have typed the whole formula in the calculator. The only that is missing is pressing the equal sign. So I press the equal sign and I obtain that this is 0.039840105. This number that we have in the calculator, is the number that I'm going to use here for I. If we have a general annuity, we're going to compute the I in this way using this formula. So the answer for I is 0.039840105, and this is the one that I'm going to put here. A good idea will be to put this number in the memory of the calculator. If you put this number in the memory of the calculator, it will be easier to use it anytime we need to use it twice, and it have a lot of decimals. It's not a good idea to round this number, because rounding this number means that you're going to have some errors at the end of the result. So it will be better to use all the decimal places that we have in the number, and if we put the number in the memory of the calculator is going to be using even more decimal places, because usually in the memory of the calculators they have more decimal places than in the screen. So the number is longer than this, and the calculator have more decimals places inside the memory. So it will be a good idea to put this number in the memory of the calculator. How? Almost every calculator have an store key. Here, this is the sharp 520, I guess, and it have this store key. So it will be for storing the memory, and the calculator has several memories, A, B, C, D, etc. The thing that you see here in green. So press store key. You press the store key, you notice that appears in the screen this alpha, and then store key and choose one memory. I'm going to choose this memory A. So I'm going to press this key A, and it will be, so you see what happened in the screen. The answer is going to the memory A. So this number is the number that we have in the memory of your calculator for I. Anytime that I press recall A, it will appear this number. So you don't need to write this number several times. Okay, so let's use this number to compute the future value. Notice that even if we delete everything in the calculator, if we just press this, we clear the screen, the number will continue in the memory of the calculator. So this is I can put it in the formula, but I also can use the number that we have in the memory of the calculator. Let's do it. So let's see the formula of the future value. So to compute the future value, the only thing that we need to do is just make a substitution. Substitute every value that we have in the formula. So we're going to have something like this. The future value after 72 payments is this. So I have to just make a substitution of everything in the formula. And then use the calculator. Yeah? So when I use the calculator, I notice that there is a 60 here. So I press 60. Then open bracket. When I can open bracket. Notice when I open the bracket, immediately the 60 and the bracket go to the screen of your calculator, at the top of the screen. Then there is another bracket. All the brackets in the calculator are the same. So I'm going to open the bracket. I know that when we are writing, we use a square bracket or round bracket, but we have only one type of bracket in our calculator. Then 1 plus this number that is too long to write, and we don't have so many decimals still here. Yeah? So let's typing this number one by one will be, it's a possibility of making a mistake. So it will be a good idea to use the one that we have in the memory of the calculator, that is here in this A. I'm going to press the key recall, and then the memory A. Recall. As soon as you press recall, you notice that appears this alpha in the screen. And then the memory in which you have been input the number, and then we input the number in the memory A. So we're going to have here immediately the number that we have in the memory of the calculator. Okay, close the brackets. Just notice this bracket. And you notice that in the screen of the calculator appears the letter A. We're actually writing what we have here, 60 to bracket 1 plus I, but this I is actually the number in the memory of your calculator. You use A as a memory. Okay, to the power 72, so to the power 72. And then minus 1. And close the bracket. So close. The first bracket is crossing now. And divided by, again, this number is the one in the memory A. Divided by A. Recall A. And press equal. You're going to have the answer. So the answer is 4,991.927704. So that means that this annuity will amount to 4,991.93 cents. So this will be the answer that we have for this problem. I think with this I finish my explanation. Thank you.